So welcome back again. I hope you had an interesting visit to the labs and know the place now. We start now with the second lecture, Elements of Smart Structures. So this lecture is called like the course in total. Some confusion, so we are still before lunch and having lunch after this lecture. So what is the structure of this lecture? We will have a short introduction, then look at some objectives of smart structures, shape control, precision enhancement, noise reduction, vibration control, and integrated structural health monitoring. And then we will introduce the elements of smart structures and also have a look at adaptive systems or a bit system theory maybe. And then we have some time to clarify open questions. So as sure, yeah. As I already told, for the preparation of the exam, I have these learning objectives in front of every lecture, and you will also get the slides, I think, in the evening, maybe after. Okay, after the complete course. Okay, I thought I arranged with Professor Chauhan that they can get it at the end of the day. Would be possible? Okay. So then you can have a look also at the end of the day and the lecture slides and the learning objectives and so on. So what are the learning objectives of this lecture? The learning objectives are that you know the goals and application areas of smart structures / adaptronics. So our institute is called Institute of Mechanics and Adaptronics, which is a German word for smart structures. I will get to it in a few minutes. Then a goal is that you can explain which elements or building blocks are needed for adaptronic systems or smart structures and what types of systems we can distinguish. Then you can distinguish adaptronics or smart structures from mechatronics, which is closely related. You can explain fundamental principles of adaptronic systems using examples I will introduce. And you know the 6 levels of integration of adaptronic systems and can also describe their differences. And you can identify the engineering challenges due to the trade-offs in adaptronic systems. So a bit of a historical background. There was a first patent published by Luc in the year 1933, and it was about influencing of one-dimensional sound fields. So it is more or less the original patent for active noise control and also for the active noise cancelling headphones you may all know. And since the mid-1980s, there's intensive international research on smart structures, and these activities focus in the USA, in Japan, and in Germany. And the focus also of this course, Elements of Smart Structures, are self-adaptive structures in mechanical engineering. So may I ask, what is your background? Are you all mechanical engineers, or do we also have aerospace engineers here? Some aerospace engineers, yeah, okay. Rest is mechanical engineering, or do we have something else? Sorry? Electrical engineering? Civil engineering? Okay, also civil. And you? Sorry? Okay, mathematics. So we have, quite a mixed audience, which is really nice. So several related terms emerged as mentioned. In Germany, we say adaptronics. We also use smart structures, but adaptronics or adaptronik is the German word. And we also have intelligent materials, intelligent structures, or intelligent systems, as well as adaptive materials, structures, or systems. And they are more or less used exchangeable, so like synonyms. So what are smart structures? They compromise essentially 4 target areas. You may all know this figure already from the posters. So we have active shape control, like this droop nose from a leading edge of an aircraft. We have structural health monitoring, the ability that a structure knows its state and may identify damage. Then we have active noise cancellation, like in the first patent, and we have active vibration reduction or active vibration control, and these 2 topics are, I think, closely related, and all of them influence the elastomechanical properties. And in this lecture, we will go through some examples in the different fields. So now I want you to maybe discuss with your neighbor in 2 minutes what you think is the difference between smart structures or adaptronics and mechatronics. So I ask you to discuss what could be the main difference between mechatronics and smart structures. And we may take 1 or 2 minutes to that you have some time to discuss and maybe introduce yourself to your neighbor if you are not familiar, and then we collect 1 or 2 answers and then we go ahead. What could be the difference between a smart structure and a mechatronics structure? Okay, the difference is the main difference is the degree of integration which distinguishes adaptronics or smart structures. I also used the term a bit mixed, so I replaced it in most of the cases to smart structures, but not in every place. And the difference is the degree of function integration. When in a mechatronics systems, you have also sensors, actuators, microprocessor or controller, and an amplifier for power supply, like in smart structures, where you also have a sensing material and an actuating material, a controller and a power supply. But in smart structures, these elements are integrated into the load-bearing structure and not differential additional elements like in mechatronics. So who came to a similar conclusion while discussing with their neighbor? Yeah? Okay, good. So what is adaptronics? I used the term already a lot. It's a coined term made of adaptive and electronics, means adaptronics, and it was introduced in 1991 in Germany by an expert working group. So it's quite a German word. And this is an interdisciplinary field, focuses on adaptive, self-adjusting structures which can actively respond and reuse, as seen on the slide before, integrated sensors and actuators directly in the load path. So it is part of the load-bearing structure. And this is the difference to mechatronics. We have the functional integration into the structure. And at least one element in this control loop should be multifunctional. We will also come to the definition of functional and multifunctional later on. And the aim really is to create intelligent structures through this smart material behavior. Here again we have the droop nose and also an active rotor blade, which is introduced in a few slides. So we can state a scientific paradigm of adaptronics, which is the investigation of load-bearing technical products from material systems to machine elements, devices to plants, with properties of biological adaptable systems for the purpose of mass and energy saving and the production of adaptability to different environmental conditions. So the important part is that we want to save mass or energy and we want to adapt to different environmental conditions. And the technical paradigm is more characterized by the investigation of all questions of the integration of actuators and sensors and also the control into the material or the structure itself. And here, for example, we see a complex shaped piezoceramic actuator. We will learn more in the day after tomorrow, I think. I have also some literature notes brought. There is a book by Professor Zinapius, Adaptronics and Smart Structures, Adaptronics, Smart Structures and Materials. On this book, this course is mainly based on, so if you would like to look up something or deep dive into some topics, you can have a look in this book. Professor Zinapius was also 2 times here, also giving GIAN courses. And there are additional books focusing on more specified areas, like this book from Ruschmeyer on piezoceramics, or the book of Bar Cohen on electroactive polymers. So you get an introduction to the literature and can look something up if you like. So now we come to the smart structures itself. And first we look at shape control. The example I've brought is in high precision or the high precision shape control of a satellite reflector. And the challenge or the problem is the one-sided thermal loading of this satellite reflector, which alters the reflector focus due to the induced curvature. And the idea or the research approach was to have a CFRP-centric structure with integrated piezoceramic actuators, which then can deform the reflector itself and compensate for the unwanted deformations. And in this schematic, you can see this reflector. We have an actuator here and a sensor here, which collects a sensor signal, which then goes through the controller, and the controller creates a signal for the actuator. And the challenge is that we have a perturbance, for example, airborne noise or the thermal loading. And due to the sensor signal, the controller tries to get a structural response without the perturbance. And here below you can see the different elements of this satellite reflector. Here are the piezoceramic transducers, which are then integrated into the reflector structure, and then thereof the whole system is made from. The next example of shape control is on helicopter rotor blades. There was a project at DLR, or several projects. One is still ongoing on this topic. The challenge is that each rotor blade of a helicopter collides with the vortex generated by the one ahead, so by this one. And these collisions between the rotor and the vortex from the rotor blade ahead generates noise and also strong vibrations. I think you all know the typical noise of a helicopter. And here the research approach was to have an active twist rotor blade, where you can deform the rotor blade a bit and change the angle of attack slightly of the rotor blade, so that the rotor blade does not hit directly this vortex. And this was done by integrating of surface actuators into this anisotropic rotor blade skin made from fiber composite structures, so carbon fiber reinforced plastics. And in now the rotor blades are already tested in a rotor test bench, but here are some simulation results, preliminary simulation results. You can see the area of the rotor from the top, so X and Y coordinates, and this is the normalized lift of the rotor in total, and this shows the normalized lift with the system turned off, so a passive rotor blade, and you can see this red areas where lift is higher than the average lift, so it's normalized to 0. Lift the average lift is 0, and these red areas are areas where we have higher lift, and therefore also this generated noise and vibrations. And the figure here below shows the active rotor blades, so the controller is turned on, and you can see that that these red areas are not vanished totally, but are smaller in extent. So the active rotor blade is working, and this was also substantiated in tests already. Then the next field is precision enhancement, which could also be, let's say, sorted in vibration control. It's on handling technologies or robotics. Here is the challenge that in parallel robotics, like this robot, where the manipulator is here in front, you have fast movements, and if you stop these movements and brake, you have vibrations here at this place, which decreases the precision of the parallel robot. And there was a collaborative research center, an SFB, Sonderforschungsbereich in German, between TU Braunschweig and German Aerospace Center, DLR, between 2000 and 2010, where the focus was to have technologies for precision enhancement of these parallel robots. And the approach was to integrate active struts with piezo stacks into the structure. So these struts were replaced by active struts. And then again, we had a control loop. So we have a sensor which senses the acceleration here at this point. And then again, a controller and generating an actuator signal for the active struts. And the result was that at 4 eigenfrequencies, the vibration could be reduced by maximum of 20 decibels. And here you can see also a real picture of these parallel robot with these active struts, where you can see in slightly orange the piezoceramic transducers. So then we move over to noise reduction, also a field of smart structures, using the example of a passenger car. You have several sources of noise for the interior, for the passengers. You have the oncoming air. You have the combustion engine, and also the blower and the heat exchanger, at least when you have internal combustion engine cars. With battery electric vehicles, you don't have this noise, but you still have the noise from the tire-track interaction, and if you have a combustion engine, also from the exhaust. And all this impedes the ride comfort. And here one slide is missing, but I can explain it here. So the idea is to have a microphone here installed in the interior, and active piezoceramic transducers at the car roof, and then let's say the disturbance signal, the noise in the cabin was recorded, and a signal for the piezoceramic transducers at the roof was generated, and with this the whole interior was had a noise reduction. in the future applications, I also have at the last or second last day, I also have a similar example for an aircraft cabin with a lining, active lining. Also noise reduction. Don't know if somebody already has been into a magnetic resonance imaging machine. I've not been, but I heard that it's very loud inside, especially when your head is inside. The idea was to have an active cylinder here, also with piezo patches and a control and adaptive filtering, which was then placed here. And with this, also the noise could be reduced by 25 decibels to increase the comfort of the patient and that he won't move during imaging. Then for vibration control, I have another example from transportation engineering, an adaptive convertible. So here's a car made 20 years back from Mercedes-Benz, a convertible. And the problem there is, or the challenge, that with a convertible you have a missing roof, and this reduces the body stiffness and introduces some torsional vibrations during the ride. And this is excited by engine and also by the chassis from the suspension. And you could stiffen the car body underneath and add mass and structure. But here the idea was to use again active cross braces with a controller and also a sensor. You always need these, so a sensor, actuator, controller, and energy supply. These struts were comparable like these struts in the parallel robot. And it worked out, so it improved the ride comfort, the adaptation, and you don't need any mass for tuning. I have a graph here. Maybe it's a bit small. So this is the amplitude of the vibration, and here are the frequencies. And in black you can see the vibrations without the control loop. So the controller turned off, and at 15 hertz you have a peak here in the amplitude, and with the controller turned on, the peak is gone. So you can control the vibrations at torsional mode at 15 hertz. And then the last objective, or the last application area, is integrated structural health monitoring. Here the challenge or the problem is that safety relevant components must be continuously monitored to ensure their structural integrity and functionality, especially in aerospace structures. You have, or in commercial aircraft, you have the different checks, A, B, C, D check, and inspection intervals. And here the idea is to, let's say, have not a maintenance for the schedule, but the maintenance when it's really needed, when you have a damage in the structure. And for that you have to know which damage you have in the structure and where. And this is done by structural integrated actuators and also sensors. So in a laminated composite you can integrate the actuators and the sensors. We will also have a look on that, how to integrate them into fiber composite structures. And the idea here is to excite the structure, guided waves in these thin structures. And if you have a damage in the structure, the damage causes a stiffness loss, which then has an impact on the of the wave velocity or wave propagation. And this you can measure. And if you have more than one sensor actor pair, you can also triangulate the location of the damage. So the idea is that the damage changes the wave propagation and with the changed wave propagation, if you have a baseline signal or baseline behavior of the structure, then you can say if there is a damage inside or not. So to sum up the objectives before we go over to the elements, we try to influence the elastomechanical behavior by activatable, integratable materials and fast controllers. And with this, we adapt to diverse environmental conditions like active shape control, active vibration reduction, active noise cancellation, as well as structural health monitoring. And we saw examples from all 4 areas of this figure. So now we go over to the elements of smart structures itself, what is really needed to build up these structures. I've brought this kind of figure, which are is made of rings from outside to inside. We lead smart materials, for example, piezo ceramics, for the sensors and the actuators. Here you can see the piezo ceramic materials as an example, and this is also the first topic we will focus on, the first element we focus on. It's the piezo ceramic or the functional materials itself. From this you can build up multifunctional elements. So the piezo ceramics could be embedded in polymers, and then you create this kind of transducers, piezo composite transducers, which have load-bearing capability and also sensory or actuatoric properties. And then the next element, at the example of the satellite reflector, is the adaptive lightweight structure itself, where these multifunctional elements, the piezo composite transducers, are then integrated into. And this adaptive lightweight structure is then part of the adaptive system itself, with the power supply and also with the controller. So here, plus control and plus energy. So now we will have a look at adaptive systems. A schematic of the operating principle of an adaptive system or the overall system. We already saw it at different examples, but you have a structure, load-bearing structure, which is also the difference to mechatronics, that actuators and sensors are integrated into the load path. You have a structural excitation, for example, structure-borne vibration or airborne sound or thermal loading, which is impeding or disturbing the structure. This disturbance is collected by the sensor or recorded by the sensor, and the sensor signal then goes through the controller to the actuator, generating the actuator signal and then controlling the actuator. And the result is a structural response, which is without the structural excitation. So you, for example, control a vibration in this case. So looking at the systems, we could have an ideal passive system, so a technical adaptive system where we convert inputs to outputs, for example, energy, substances, or signals. This technical system then maps an input quantity to a desired output quantity, or we can simplify it, just input goes into the technical system and then we have the output. This is the ideal system. What we really have is a real passive system at first hand, where we have this kind of disturbance, and then we won't get our desired output or our target directly, because we have the input into the technical system and also the disturbance, and then our output has a deficiency. So there is not we will not get our target output alone. As an example, the satellite reflector fulfills its function when it transmits signals, but due to the deformations from thermal loading, we have a disturbance and maybe the signal transmission is impaired. So what could we do? We can build adaptive systems which suppress these kind of malfunctions, and they differ from passive systems in that the objective function is specified and malfunctions are prevented by the adapting the system properties. And for doing so, we have two options. We can measure the disturbance directly and feed them back through a controller into an adaptation parameter into the adaptive system, or we can measure our output quantity and not the disturbance and feed that back through the controller into the adaptation parameters and then have the output. I'm sorry, I have some German words here on the slide, but I hope it will work out nevertheless. Yeah. So the second kind of system is a system which has varying properties. So in this case, we have an adaptability not to compensate for disturbances, but to switch between different system states. So we can switch between objective functions in response to external conditions. We have a condition and here a system state, and then we can switch between target function A and target function B, and therefore our input is then converted in the adaptive system to output A or B, or as a function of the target function A or B. And an example could be a joint, which is designed to switch between a blocked and a movable state. Do you have other ideas what could be such kind of a system? Not necessarily a smart structure, but maybe do you have an idea what could be an example for these kind of systems? Maybe the aerospace engineers here have an idea. Okay, one idea could be the droop nose we saw, or more traditional high lift devices, because then you can switch the aircraft state from cruise flight, where you want to reduce drag and do not need so much lift, to the start and landing phase, where you need high lift coefficients and the drag is maybe not so important because you are not flying that fast. It would be also these kind of adaptive systems where you switch between target function A and B, takeoff and landing, and cruise flight. And if we take the droop nose for this would be also a smart structure. And in the future applications, I also have a smart structure leading edge. So then one learning objective was to distinguish different integration stages. We can distinguish in total 6 integration stages. So level 1 is actuator or sensor integrated or applied to the load-bearing structure, and the other part is an external component, like in mechatronics. This would be level 1. Level 2 is the sensor, for example, applied and the actuator integrated. So one part integrated, one part applied. And level 3 is both sensor and actuator integrated. We look also at structural integration, and for these kind of systems, so level 2 and 3, where at least some parts are integrated, fiber reinforced plastics are yeah, a good choice, because there the integration is far easier than in metals as the base structure. Yeah, so if you have, let's say, a metal structure, you can only apply things. You have the level 1, for example, the parallel robot. And here's also an example of the car roof I showed for noise reduction, where you can see here the car roof from inside, and which is made from metal with the applied piezo composite transducers. For the lightweight mirror from the satellite reflector, this would be level 2 with integrated actuators, and level 3 made from carbon fiber reinforced plastics with sensors and actuators integrated. This is the case for the helicopter rotor blade. And then we have the levels 4 to 6, which are not, let's say, part of this course, but for completion, we have level 4. Here also the signal processing is integrated in the load-bearing structure. So not only sensors and actuators, but also the signal processing. Then level 5, additionally, also the controller hardware is integrated. And then in level 6, also the power electronics is integrated. So in level 6, really every part of the smart structural system is integrated into the structure. So then I think the last learning goal was about the challenges or trade-offs in smart structures. And we can have a look at it at the example of the helicopter rotor blades, because you always need to do or to have trade-offs when you have high degrees of integration. Because at the example of the active helicopter rotor blade, you need basically a high skin stiffness for to bear the aerodynamic loads and to have a good structural system. But you need rather low stiffness to be able to deform it, to have these ±2 degree change in the angle of attack of the rotor blade. So you have also you have to trade off a high skin stiffness for the load bearing purposes, and the low stiffness to be able to deform it, and have to find an optimum or a trade-off between these two. And another trade-off or conflict in objectives is the multifunctionality. If you have a structure with an integrated structural health monitoring system, you can, at least in theory, build the structure lighter, because you know damages, and you don't have to have so much margin in safety for the inspection intervals. But you also introduce mass in the systems with the sensors and the actuators, and maybe also the other elements like energy supply and controller. So if the structural health monitoring system is heavier than the mass saving you generate with it, then maybe this is not a successful smart structure. Okay, so with this, I'm at a summary for this lecture. We saw the goals of smart structures illustrated by examples. Then we learned about the elements of smart structures, the name-giving elements of this GIAN course, which are materials, multifunctional materials. Then we have elements, structures, and the whole system, which is built from sensors, actuators, controllers, and energy supply. We had a look at integration levels and the definitions of the levels 1 to 6. We discussed a bit about the distinction between smart structures and mechatronics. And we also distinguished two different adaptive systems, one with varying properties, like the example of the aircraft, high lift phase and cruise phase. And the other case is the malfunction suppressing adaptive system, for example, the the satellite reflector. So do you have questions on this content? Yeah, so the actuator is the part which, for example, deforms the structure. You give a signal to the actuator and then it deforms, and with this you can influence the elastomechanical properties. And the sensor is the part where you record or collect the information about disturbance, for example, which then is compensated with the actuator. But we will go more into detail in the next lectures about the sensors and actuators itself, especially made from piezoceramic materials, so piezoelectric effect. Mm-hmm. Yeah. The controller part is not the focus of this course, and to be honest, I'm also not an expert in control theory. So we are focusing on the structure, on sensors and actuators, and also on application examples, but control will not be part of this short course.
So the reflector parabolic shape,
yeah.
Temperature changes.
Yeah.
So how this actuator we can suppress the malfunction?
Right? Yeah. Yeah. So the idea is if you have the one-sided thermal loading, then the reflector deforms a bit and it loses its reflector focus, or the signal transmission is not that good like in the previously defined state. And with the integrated actuators, you deform the reflector back in the wanted state so that you have good signal transmission. Yeah.
Smart structures are different from smart materials.
Mm-hmm.
Tell all various types of smart materials.
Mm-hmm. We will have a lecture on different smart materials. So this course focuses on piezoceramics, but we will also look at electroactive polymers, and also multifunction materials would be smart memory alloys or smart memory polymers, but this will not be, let's say, a focus part of this short course. Yeah. And the smart structure is then the whole system with energy supply and controller. Yep.
Like how piezoelectric ceramic lines in an MRI that you showed reduces the sounds.
So how thick the actuator is? I think around, so it depends on the actuator. I think there are maybe up to 1 millimeter in thickness, but I don't. Do we have brought some actuator? I think not. We missed it, right?
Only applied actuators.
Only applied actuators. Yeah, we will have applied actuators in the lab, and maybe we will bring it to the lecture, and then we'll show afterwards so you get an impression how the dimensions are. Yeah? Okay. Okay. Further questions? Yeah?
Do you have any example of level 5 or 6 integration?
Not brought with me, I think. I can check if there are some ongoing projects at DLR, level 5 and 6 integrations, but I'm not quite sure. In this Institute of Lightweight Systems, there's one department, Adaptronics, who's working on all these smart structure things, and in the future applications, I have briefly described some of their ongoing projects, but I'm not sure which integrations level they use at the moment. Yeah. Okay. Then now we finally have the lunch break. Thank you very much.